Oh, hi. My name is Craig Waters. I'm going to talk to you today about the anatomy of an SSD. I'll just get straight into it. I know we've only got 15 minutes, so thanks for listening, and here we go. So all SSDs are manufactured the same way. The only really difference is the number of bits that are stored in each cell and the amount of capacity that's provisioned. So, the number of bits in each cell really basically equals more capacity. So you're probably aware that the different styles of SSD that's been used in consumer and production spaces at the moment. So we've got single cell, which has 1 bit per cell. We've got enterprise MLC, which is 2 bits per cell. Typically enterprise MLC, and the difference compared to normal MLC is just the overcapacity that's been provisioned. So typically you buy an eMLC in a 400, 800 or 1600 gigabyte capacity, when in actual fact they're actually provisioned for 512, 1024 and 2048 gigabytes. Then you've got the normal MLC as well. Again, it's just 2 bits per cell. And you've got triple LLC, triple layer cell with 3 bits per cell. And I've heard recently discussions on quad layer cell with 4 bits. So that should be quite interesting. So I think what's probably quite an interesting point about SSD is the fact that NAND Flash itself is analog. So how bits are actually stored in NAND Flash is via a voltage. A voltage is applied to that cell, and then the state of that voltage determines whether that cell's bits are a 1 or a 0. So you can see there with SLC, 1 bit equals 2 states, 0 and 1. MLC and eMLC's got two bits, so you've got 4 states. TLC's 3 bits, so you have 8 states. And I've got a nice little table there that then kind of calculates out the amount of capacity based upon an SLC and an MLC and a TLC. The mediums, the cell, pages, block, and plane, I'll go into in a second on the next page, yeah. But so you can see there how it actually works is we've got about 32,000 cells in a page, and then 128 pages in a block, and then 1024 blocks in a plane. And then you can see there the actual NAND Flash die is made up of a bunch of planes all stacked together. You probably heard of the term recently 3D NAND Flash as well. Well, that's basically the NAND Flash dies being stacked on top of each other as well. So you've got to love the marketing guys with 3D. But ultimately, this is just all about capacity and increasing the amount of capacity in a NAND Flash die. So what I've also got there is an example of a couple of different SSD types. You've got there an SLC that was manufactured in 2012, an MLC in 2014, and a TLC in 2015. Interesting to see the capacity changes. So the SLC's got 8 gig NAND flash dies. The MLC from 2014's got 64 gig NAND flash dies. And the MLC in 2015 is actually 128 gig NAND flash dies. So let's have a look at the anatomy of each of these. So you can see there they've all got controllers. The newer ones, the MLCs, have got ARM controllers. The SLC's got I think it's a SandForce. And we talked before about how we're actually storing the bits in each cells based upon the voltage. So they've each got quite complicated power components in there, and you can see the changes in the technology just in a couple of years. The SLC's got surface mounted capacitors there, where if you look at the newer ones, they're actually printed directly onto the PCB, the printed circuit board, whereas with the older one it's actually surface mounted, so it's added on at a later date. And then of course you've got the actual NAND flash itself. So I talked about the capacities before, and what's quite interesting is with the 2015 MLC, you can see there that that's actually that 3D. So what you've got is 2 NAND flash dies actually sandwiched on top of each other to give you 128 gig. So really, it's very similar to the 64 gig. They're just that much more thicker, that much more denser. Some of the other interesting points as well is that the MLC drives are both they're printed on both sides of the printed circuit board, whereas you look at the SLC, it's actually just on one side, so you turn it over and there's no componentry on the other side of the PCB. And I think what's also kind of interesting is they're all SATA 3 interfaces as well. So we've gone a big change in capacity from 2012 to 80 gig all the way to 2015 to 1 terabyte, and yet we're still using the same interface, the SATA 3 interface, which is quite interesting as well. So this is a blatant plug of my blog. Back in November last year, I went and actually visited a NAND Flash manufacturing facility, and the interesting point is that it's more about assembly. So this factory was actually based in downtown Santa Clara in Silicon Valley, and you think, well, what are they doing manufacturing flash in Santa Clara? But it's more of an assembly point. The NAND flash fabrication is actually done in Asia. It's probably in Korea or Japan or somewhere like that. What's interesting about this particular picture here is, we talked before about the power circuitry and them actually printing the transistors directly onto the PCB. Yeah. So what you've got here is this is the machine that actually prints those the transistors directly onto the PCB. So you've got these tapes. They've actually got tapes there and big rolls of resistors that actually get printed on. So what's really good to know is that the actual process is completely automated, but there's still a lot of humans involved because they're actually doing Q&A. So we have a life beyond when the machines take over. We're still going to be needing to do Q&A for the machine, so that's a reassuring piece, yeah. So I want to then just talk a bit more about why we need to treat NAND flash differently compared to traditional spinning disks, yeah. And really it's about this concept of the program and erase cycles. When you buy an SSD, it's completely empty, there's nothing in there, but over time as you fill it up, there's a couple of things that you kind of need to take into consideration that's unique to SSDs, and that's this whole concept of wear leveling. So we don't want to write to the same cell all the time because that cell's going to degrade very quickly. And what we want to do as well is we want to write to empty cells all the time. We don't want to be shifting cells around over time. So really have this concept of garbage collection. Garbage collection is a background process which basically it solves this problem around NAND flash by the fact that we can read and program on a page, but we can only erase on a block level. So I kind of talked about the sizes earlier on. So we can read and program on a really small scale, but when we actually come to erase that, we can only actually do it on a block level, and that's kind of where write amplification comes into place, because basically with write amplification, we have to read all the pages in a particular block, and we have to relocate those pages to another block before we can erase the block. Yeah. So that's really what garbage collection's doing. I've got some examples. Thanks Wikipedia for this. So you can see the example on the left here is garbage collection in effect. So pages A, B, and C are written. And then what happens is some new data is put on there, E, F, and G's and H has been put on there, but then A, B, and C and D's states changed. They've been written again. Now, the only way we can free up that block is actually to move all that data. So garbage collection works as a background process, and it looks for all these blocks where there's data that's no longer current. And what it'll do is it'll read out the current data, and it'll actually move it to a new block so that then that data can be erased. And we've also got there an example of write amplification as well. So you can see then in that block there's all these 4K pages, and they actually have to be moved to another location before that block can be erased. Yeah. So I want to just finish off really looking at how Flash has been implemented in the enterprise at the moment, and really the idea is just to look at this as an independent view and determine what the considerations are for the different types of Flash implementation, and just some points that you probably need to consider if you're looking at one of these options. So we've got 3 different kinds here. First of all, we've got Retrofit, which is basically the concept of a storage array being utilized that was originally designed for running spinning disks, but what's happened now is that pretty much all the spinning disks have been removed from the controller, and now they're using SSDs instead. So what are some of the pros of that? I mean, first of all, I think it's important to know it's a known product. So it could be an existing vendor that I've used previously. I've got the management details for that. I know the processes around managing it on a daily basis. Another example here for the pros is also that easy upgrade path. So I'm already using the product. It's going to be quite easy for me to move from hard drives to SSDs. Yeah, but some of the cons, and I think this is kind of quite a big one really, is the concept that the controller software has really been programmed to address hard drives and not SSDs. So the controller software is really going to be looking about head management and platter positioning, those sort of things, whereas that's not going to make any sense from an SSD perspective. It's not really going to be needing to know that information. The other con as well is that lack of SSD-related software features. So, with using SSDs, it means we've got that, extra performance, so we can do some interesting things like, I don't know, maybe do some data reduction or something like that. Yeah. Next one's a hybrid. So what's a hybrid? Well, basically that's where we're combining SSDs with hard drives. So, and there might be an SSD tier in the array, or it could be a cache or something like that. And then we've also got a hard disk drive capacity tier as well. Yeah. So some of the pros of that, well, you're purchasing less SSDs, so surely the solution should be cheaper. Yeah. And also, hard disk drives are being used to provide capacity as well. So a greater capacity could potentially be provided as part of that solution. But let's have a look at some of the cons, and I think this is probably a fairly big one, is well, first of all, there's the tiering may be difficult to manage. Some storage solutions don't necessarily provide auto-tiering, and it's down to the administrator to actually manage that overhead. The other one as well, I think it's quite a big one, is the whole concept of dealing with the active working set. As an administrator, do you know what your active working set is? It can be quite challenging to calculate, and obviously you need to make sure that that your active working set fits within that SSD tier, because as soon as it spills out of the SSD tier, you're going to have a performance impact to your workload. Yeah. Finally, we're all flash. Yeah. So what is all flash? Well, it's simply that the whole array is using SSDs. It's not using hard drives at all. So what could be some of the pros of that? Well, workload consolidation. So as soon as I have that performance there, it may mean that I can actually consolidate different workload types. So virtualization of desktop virtualization, server virtualization, databases. I can actually have a single solution that has enough performance and capacity to meet the requirements of all those different workloads. Yeah. Another pro might be that that you've got sufficient performance there to provide some additional SSD benefits. So things like data reduction, and potentially doing that data reduction in line as well, and not as a post-process. Yeah. But what could be some of the cons of all flash? Well, cost versus capacity. So I think it's a big one. Like if I'm buying SSD, is it going to be at a different price point to hard drives? So what do we need to consider there for the overall cost of the solution? Another good con as well is excess performance. Do I really need all this performance that an I/O that an all SSD array provides? Yeah, do I actually have a use case for that? Yeah. So I just want to finish on this slide. Really, this just overview of some of the benefits of flash. Some of them are probably you're aware of. Some of them may be less well known. Yeah. So we've got predictable performance. Low latency, high bandwidth. We've got reduction in power and cooling. Also in rack space as well. We've got increased hardware lifetime, so there's no moving parts, so that could increase the longevity of the array itself. Yeah. We talked about inline data reduction as well, so having the capability to do compression and dedupe inline. Workload consolidation as well, we talked about that. Simplification of management, so we're actually managing a solution based upon capacity and not necessarily on performance, so we may not need to look at things like RAID groups and aggregates, those sort of things. I think the final one as well, mass parallelization of I/O. So reads are free, but writes can cost. Some storage